physicists. Welcome to some wave equation practice. So hopefully you have gone through the lab that established the wave equation, and now we're going to figure out how to use it. So just a note here that the wave equation is found on your equation sheet. It's written as V is equal to F times lambda. Just a friendly reminder, and you may want to write this down too, that that is also equivalent to lambda over T, because F is equal to 1 over T. So you might want to write that down just to remember that that's a easy conversion if depending on what your givens are. Okay, let's look at a couple of examples here. This first one says a wave has a frequency of 50 hertz and a wavelength of 10 meters. What is the speed of the wave? Now, compared to some of the math, like the calculation problems that we've done this year, these are pretty straightforward, but we just want to make sure we've got it. So here we go. We're going to write down our givens, which is a skill that you have mastered at this point, I hope. So the frequency is 50 hertz. The wavelength is 10 meters. And then the unknown is what is the speed of the wave. We've got an equation. We have it highlighted right over there. V is equal to F times lambda. And so in this case, literally, we just need to plug it in. So we're going to say 50 hertz times 10 meters. And even without a calculator, I've got that one in my head. That is going to be 500 meters per second, which is the velocity. Just really quickly to make sure that those units make sense, because it seems a little strange. Let's just take a look. So a reminder that hertz is 1 over seconds, and meters obviously is meters. That's where we get our meters per second. All right, let's take a look at the second question here. It says, a piano emits frequencies that range from a low of about 28 hertz to a high of about 420 hertz. Find the range of wavelengths in the air attained by this instrument when the speed of sound in the air is 340 meters per second. So we're going to approach it the same way we did the last one. Start off with our givens. This one gives a range, which makes it a little bit more interesting. It's really just secretly two problems in one. So we're going to have a low frequency FL of 28 hertz, and you could write that as frequency 1 if you want. It doesn't really matter. And then the high frequency FH, or again, you could just write frequency 2, is 420 hertz. It says that the speed of sound, that's V, is 340 meters per second. And in this case, our unknown is the wavelength. So we're going to actually do wavelength 1, or wavelength L, keep it consistent there, and wavelength H. We've got our equation, V is equal to F times lambda. We're going to solve that for lambda, so it's going to be lambda is equal to V over F, and then we can just plug these in. It's just going to be pretty much the same process twice. So this first one for FL, or lambda L, is going to be 340 meters per second divided by 28 hertz. And we can plug that into our calculators. Go ahead and do that with me. So it's going to be 340 divided by 28, which gives us about 12.14. The units here, it's a wavelength. Remember, that means kind of from the distance for one cycle. That's going to be in meters. And then let's do lambda h. So lambda h, it's going to be the same process. So that's going to be 340 meters per second again. Because, and this is very important, the speed of sound in the air, the medium hasn't changed. And if the medium doesn't change, then the speed doesn't change either. So 340 meters per second divided by, this time it's 420 hertz. The frequency is much, much higher of those high keys on a piano than the low. So we got 340 divided by 420, and that's going to be 0.81 meters. Okay. One thing to note here, this shouldn't be a surprise, especially having worked through your lab. But one thing to note is that as the wavelength goes down, the frequency goes up, right? Here we've got a higher frequency. I just said that, well, I said that correctly, but I underlined it backwards. I apologize. As the frequency goes up, the wavelength goes down and vice versa. They are inversely proportional. frequency, and wavelength because they always have the same product. Hope this was helpful. Have a great day.